So anyway, last class we have discussed about hashing. Hashing is basically one external, searching technique, right? External searching technique, which is the other way around. I can say an extended array, because how we are implementing hashing with the help of hash table, rather, right? If you could have seen, yes. This hashing was basically implemented with the help of a table, right? So this I can say is an extended array. The other way around, we call these kind of arrays are associative arrays. When you have multiple, elements for every entry, which helps to search and retrieve the respective entry over it, we call such kind of arrays are associative arrays. So the other way around, I say extended arrays are associative arrays. So we have seen by extending the arrays, right, as an associative one, we can rather implement this, hashing technique, right? And we have seen hashing is giving a good result. It's giving the time complexity of around constant, right? If you see before hashing, the efficient, algorithm like binary search was giving you logarithmic, uh, time complexity, right? But then this was working good for you, and we have discussed what is a hash function, how we are going to map the records of a file to hash table, and what are the problems you result with, like the collisions and all, when you get more than one hash for more than one key. If you are mapping with the same kind of hash key value, you will be finding a collided kind of entry. So these collided entries to be rather resolved by finding an empty entry over it, for which we have some kind of collision resolution technique that we have talked about, like separate chaining that we have talked about, and open addressing. So in separate chaining, when you find a collided entry, you will simply add a node and then insert into the next field of its predecessor. That way, you can probably form a chain of collided entries at the same index, right? That was one solution, and then we have talked about other solutions like linear probing, where you are trying to find an empty entry when you are collided with certain index j, from its successor, taking a cycle until you reach get back to again the its predecessor, rather, right? Wherever you find an empty entry over this particular cycle, starting from j plus 1 till up to n minus 1, and 0 till up to n minus 1, when you get an collided entry at the index j. So that is one solution which we have found, and then there are a couple of other solutions like quadratic probing, where what we were doing, like we were adding a bit value, a value to the hash key value that we get out of it, and then again getting the hash out of it, rather, right? So it's something like double hashing the other way around in quadratic probing we are doing, rather, right? So we are adding this is a hash key value that you get out of it. You're adding some certain value which is being rather squared, and then get the mod out of it. Okay, so this particular I value is going to be varied between 1 till up to the size half of the size of the same, right? So that way you can probably find an empty entry for a collided one, and then find a room for the same, and then you are trying to fix all this. This is all what we have talked about, and we have implemented all this with the help of what exactly, by extending the array, rather, right? So now, as we have seen, the dictionaries, you can rather implement with the help of this, hashing in a more efficient way as well. That is what we have discussed in the previous class. So by taking the glance of what I have discussed in the previous class, I would like to now take on to the current class, current session. So in this session, I would like to discuss about the skip list, right? So if you look at skip list, this is also one of the searching mechanism, but the other way around, here we are extending the linked list. I hope all of you know the difference between the arrays and linked list. If you look at the way where this linked lists have been born. So I hope all of you know what is an array, what is a linked list, right? First, you have to know these basic data structures. What is an array? Yeah, what is an array basically? Array is a collection of homogeneous elements, we call it as, right? When we want to store a bunch of element at the same place the other way around and being pointed to a single name, okay? Uh, yes or no? Int A, if I say int A of 10, then so when you have huge number of elements of same kind, rather you can go with what, this, arrays. Yes or no? So here the limitations in the array, as we know, probably you may have rather studied during the data structure, dynamic memory allocation and deallocation. What do you mean by this, right? What do you mean by dynamic allocation and deallocation? Basically, why do you need actually? Where was the need of DMR came into being, rather, right? When you are working with arrays, the problem is, as you know, Unix is a Unix or Linux, which you call it as. This is an operating system, but it's a time-sharing operating system, right? So now we have got, after the advent of ICs, because of cheaper ICs, we could able to get high-end systems in the form of a laptop or a pen tab and desktop and all kind of thing. But otherwise, if you see the time when ICs were not there, the computers were being built using XTs, where it was quite expensive, and the people, basically the computers were being, as you know, were being used only at the by the academicians or by some scientists at certain laboratories, okay, defense or avionic kind. But later, after ISIS came into being, you could have seen it has been commercialized so much, rather, right? So that time, when you look at, DEC PDP is the first version of the Linux, of course, right? DEC PDP 11. Then it was upgraded to Minix, and then Linux, and we got a lot of versions of Linux. We got Red Hat, Ubuntu, GNU Linux, and Sushi, all that we have. A lot of flavors we have. Anyway, but then what where I wanted to take you is nothing but it is a time sharing operating system, right? So the time when we have studied, also we used to get shared from the server. Actually, there was a server, generally, even if you see in internet, that is there. But then the time when we were studying, we used to access the data from the server itself, right? We used to store our files on the server itself. So all these machines basically are allocated with certain space, right, in that server. So let us say this user 1, okay, this is user 2, and this is user 3. All of them are allocated with certain, let us say, 100 element space. So with the help of a stack, there's a stack space basically wherein you perform your respective operations, right? Every user, when we start executing a program and system, he will be allocated with some stack space, right? All such, basically stack is very much essential, as you must be knowing that a lot of applications of stack are there. One of such, widely, which and you see that expression evaluation. Expressions which you give in the mathematics, they are not as it is going to be rather given in the system, but they are either converted into prefix form or the postfix form. Plus AB is the prefix if you write the operator first, right? And postfix form, that is when you write the operator next, okay? So this is postfix. So either this form or that form that your computer takes based on the manufacturer, rather, right? So for which, of course, you must be having some programs which we call it as compiler, right? So your compiler does all this, of course. So here, okay. So these conversions and then evaluation and all to do, you need a stack, right? And this is a regular operation which you probably need once you start computer. Once you start, you know executing certain tasks on the computer. And in addition to that, if you have some functions calling and recursions, right? And if you have sorting, searching techniques, or you have graph towers, a lot of even for smaller function execution, or if you're switching between the modes. As you know, when you switch on the system, what happens basically? A bootstrap loader program get executed, right? When it get executed, what happens? All the OS programs are ready for providing the services, right? So that mode is said to be what? Kernel mode. And you are in the user mode, yes or no? You are in the user mode. So you are executing certain tasks. Like in C, you have system calls with the help of which you can directly go to the machine and then get the respective services. Fine. So with the help of system calls. That's the reason why C or C++ languages are said to be machine level and as well the high level. That's the reason we put it under middle level, right? It acts like high level and at the same time low. The language with which you can probably directly talk to the machine are said to be low level, right? All assembly level languages, processor based languages are said to be the low level language. But C, C++ are having the beauty that they can talk to the machine directly with the help of the system call. That's how it can act as a low level. At the same time, it can perform user tasks with the user's language, right? That's the reason why we say it is a middle level line. Yes or no? So anyway, why I am discussing all this, which you already know about it. Fine. So you need to switch all the time when you probably required to get some services from the operating system. So when you require to switch between the modes as well, you need stack, right? Where do you store the current status of your program, which is nothing but program status word we call it as, right? This you must be studying in computer architecture. Program status word consists of the program counter register value. Program counter basically holds the return address rather, right? And then in addition to that, certain processor register and flip-flop values that it has, right? Return address and addition to that some processor register and flip-flop values. Together we call it as program status word. So this program status word, where does basically you store before you switching between the user to kernel mode? On a stack, right? You'll be storing it on a stack. So when you go to the kernel and then get your task done, and when you come back again, you need to start from where you left off. It's not that you have to start from the beginning. So where you left off is being told by this PSW, right? PSW will help you to start continuing from where you left off, rather, right? So, but then that is going to be, done or implemented with the help of stack, right? With the help of push and pop operation. When you push it onto the PSW, right, it stores in the form of a last in first out kind. The same order probably you require when you are trying to push the elements over the stack, or you are leaving some things in between and then coming back again to the same rather, right? So like working of when you are working on a browser and you are trying to browse the pages one after the other, how do you go back? Will you go back to the beginning immediately, or it's or step by step? You have a back button, right? That back button takes you to the immediate next, like that. So it's the back button of your browser is also implemented using the stack concept rather, right? There are a lot of applications in all gaming program usage is a stack concept. Anyway, why I have discussed, because the stack is also one part of data structure that you have implemented as part of the lab rather, right? So now coming to our discussion here, as I said, every user in time sharing operation will be given certain space. Let us say, for example, 100 element space is given to each of the user. Now, let us say some users' capacity is more. It means he is executing more programs. Some other users may be executing less, right? So in that situation, what happens? If they're all in execution, now this user one, let us say, needs 125 element space. Okay, he has only 100, because as everyone is given only 100, he will also have 100. But then rest of the 25 element space, how does he get rather, right? See, the space which is available at the server is already divided across all the users who are connected. And the other users, if you see, probably let us say user 2 though he's having 100 space, but he must be using, let us say, only 50, not more than that. So 50 element space is left, you know, unused at user 2, and user 1 needs 25 element space. Is it possible user 2 to give user 1, or user 1 can snatch away from user 2? No, it can happen only via the, again, server itself. It means if server, because they're all connected via server, they don't have direct connections, right? These users are independent of each other, so they have to take anything if they have to take from the server side. So in that case, a solution we are here providing with the help of this dynamic allocation and delocation, that instead of allocating the memory to each of the user, based on our size at the beginning itself, rather what we do is we will keep the space, you know we will keep the space, entire space, at the server, side itself. We call this as heap, heap, heap. Okay. Now, when a user wants, during the execution time, probably they need, right, how many input they must be giving, and based on how many element space that there are the required. So this is all being done during the only runtime. So all these people will know only about their requirement of the space during the runtime. So let them execute their programs, and based on the requirement they can go and request the server and get it from the heap. So as and when they require some space, they can go and get it. When they do not need, they can release the same. So that can be used by someone else, rather, right? That way, if we adopt this kind of mechanism, then what happens is this kind of problem is solved, right? So if say user 1 require 125 and user 2 require only 50, so what happens, since we are not allocating the memory before itself, all the memory is available at only the server, and based on only the requirement, they go and fetch the required spaces from the server. So user 1 go and get 125 element space from it, and user 2 go and get the 50 element space as per his requirement. That way, both the users' requirement will get fulfilled. And some of the users, though they are allocated with certain space, but they are not at all utilizing their space, then it is all being sitting idle. So, but then what is happening here, since everything is at the central control, and whoever are doing the activity, only those people are going to be get allocated with the space based on their demand and all. That way we can utilize the memory, effectively with the help of this dynamic memory allocation and deallocation. So this particular concept is saying that based on only the requirement, and the requirement will be known only that during runtime. So during runtime, dynamically we will allocate the memory as per your requirement, right? And when you do not need, then probably you can deallocate, right? This is what the concept actually, and this concept to implement, if you see, okay, what concept is required in order to implement this particular DMA, we need a point. This is how basically a pointer invention happened, right? So let us say, for example, I said user 1 requires some space, so he will go and then fetch the required space for him. It was available at some corner. And another element probably he has encountered with, for which again another space is required. Then he must be going to heap and then requesting for another element. The other element that is going to be now given to him is not immediate to next, rather it can be any corner of that particular memory. Unlike your arrays, in arrays what happens, all the elements of the array are going to be stored in the contiguous location we call it as, right? So all are together at the same, fine, at the same place. But then if your requirement is during the runtime going to be varied, so upon your demand, based on the requirement, you will be get allocated with certain amount. But then again you require some other some other space, then probably these all different requirement that are being demanded at different instances over the same execution, not going to be allocated at the same place, rather they will be given from different places. Then in such situation, how to link these elements, right? You need some link to have a kind of coordination, so that I can start with some to access, like how in arrays it is possible. If I just know the array name, I can probably access any of the element in the particular array, because I know all these elements are stored over the same location, over the at contiguous location. So by just using indexing, I am able to access all the array element. That is what the beauty of array. So that kind of beauty, if I have to bring here, then probably I need one extra field which will hold the address of the next node, right? Similarly, every node should have a field that will hold the address of the next node, right? So that's how the linked list concept is born. But in order to implement the linked list concept, you can see this next field must be a pointer field. Why we are saying it is a pointer? It has to hold the address of the next node. So it is, since it is pointing to the next node, we say it is a pointer, and pointer is nothing but holding the address of the next node. It means it is holding the address of the same kind of element rather, right? Fine. So that's how the linked list and pointer concept is born. So you must be aware about all this, things. But then I've just taken a glance of out of all this. So this is what the basic linked list concept that you have implemented. This is there as part of your lab. You'll be implementing linked list, concept as well, and as well you are implementing linked list with the help of stacks and queues also, right? So what kind of operation generally you perform on any data structure you take? Now, basic operations are insert and delete only. What is that you do with the help of data structure? The main objective behind the data structure is to retrieve the data. Then probably in order to retrieve the data, it must have to be stored before. It means insertion operation must have been done before itself. Then you must be searching. Or another operation that you can probably do is nothing but some kind of elements you want to delete. You can go for deletion, or you want to go for some updation. These are the operations that probably find for any data structure, right? Insert, delete, and probably search kind of thing, right? In order to delete an element as well, first you need to search whether it is available or not. Only then you can go for delete. It means searching is quite important. Searching is the basic operation on any data structure you rather take. Fine. So anyway, these are the basic data structure that you are going to implement as part of your lab as well. Linked list is there, which you're going to implement, and linked list implementation using stacks and queues. You have already implemented stacks and queues using arrays. Arrays is also one kind of data structure that we have seen. Advantages of arrays are good, but then we have seen the disadvantages of arrays, right? What is the disadvantage of array? Memory effective utilization is not going to be proper rather, right? If the memory is being shared from the centralized location. So that is, in order to avoid that, what we can do is with the help of this DMA kind of concept, we can resolve that particular problem that we were facing in arrays. So this is all. I am discussing all this. Why? Because you are going to implement this in the lab as well. So probably keeping these things in mind, you can probably implement your lab sessions also in a quite efficient manner. Fine. So since you have done it way back, you must have forgot about all this. So I've just taken a glance at this. Now, looking at data structures of linked lists, if you look at, simple linked list data structure, we have seen, right? The kind of operations that we perform, like, we perform insert, delete, of course, search. These are the basic operations, right? Fine. So and count the number of nodes, and you can reverse the linked list, and you can probably concatenate, addition. The applications of linked lists are polynomial arithmetic, right? You can, if you have polynomial expression, you want to perform certain operation of polynomial, like addition, subtraction, multiplication, and all that. Also, you can implement on using the linked list. And the basic application of linked list that you must be seeing in the files. You are working with files. There is a file pointer, right? In C++ when you implement it. So file, F-I-L-E, with capital letters, you declare a file pointer in C++ in order to implement files, right? That if file pointer is nothing but what? Is a data structure rather, right? The file is a data structure. It is based on which particular data structure? It is a linked list data structure, okay? So file is an application of linked list data structure. This FP is going to hold the address of the first character of the file when you open it, rather, right? You want to search for a particular character in that particular file using scan, or you have rewind operations, or lookup operations. So this file pointer is taking to that respective character. You want to delete certain character, you want to insert, you want to append. You generally do certain operations like add certain characters to it. Like writing operation, you say you read some character means retrieving, or searching the other way around. These are some, or appending some data. So these are some kind of operations that you perform on the file, which is nothing but as a linked list implementation. So because as we know that the file is implemented using linked list, and there are many daily life applications you see of linked list. You may, when dial some customer care, there is a tone comes, right? LED tone comes and asking you to choose the language first, and then choose the service, then choose the type of complaint, choose that so and so kind of thing. What exactly it is? It is nothing but a linked list implementation, right? It's a tree. Basically, it's a tree implemented using linked list there, rather, right? So there are many applications that you probably find of linked list anyway, right? Now, what we wanted to do in skip list is want to extend the linked list. Okay, we want to, like how when we have extended arrays, we got hashing concept. We are trying to extend now linked list in order to get the skip list concept. So now moving on to skip list. Start with it. So today's session, outlined with these, contents. What is a skip list, operations on it, and implementation analysis. Okay. So now let us look at, as I said, hashing is a way to extend arrays. Fine, which probably help you to implement dictionaries and all kind of thing. Now you want to extend the linked list here, right? And to map the dictionaries, implement the dictionaries kind of concept, right? With the help of this skip list, of course, right? So if you look at skip list, it is a basically a series of lists. You can find a series of lists here. Yes or no? You have S0 starting with S0, then S1, S2, and S3. If you see each list, SI contains special keys called plus infinity and minus infinity. This is plus infinity, and this is the what is the bounds, right? The least bound and most bound, the other way around, I can say, right? So list S0 contains the keys of S in non-decreasing order. You can see the skip list basically consists of the elements in the non-decreasing with increasing order. The other way around, it's in sorted order, the other way around, right? Basically here, if you ask me what is a skip list, it is basically helping you to store the stored list of elements, right? You want to store already stored a list of elements, you are restoring the other way around, so that the searching becomes quite easier, right? Better than binary search the other way around. It's a little more similar to kind of binary search the other way, but then compared to binary search time complexity, this is further less than the binary search. Okay, each list is a subsequence of the previous one. Fine. S0 will have, S0 is a subset, superset the other way around, I can say, right? Then S1, then S2, likewise SH. SH is nothing but the height of the, skip list is going to be decided based on the H here, right? So that will decide our time complexity the other way around, right? Fine. So SH contains only two special keys, that is minus infinity to plus infinity, right? So when you're searching now in skip list, how do you basically search for an element, right? Here you can see the demonstration of the same. For example, you want to search for, let us say, 78. Okay, you want to search for what? 78. Okay, how do you search? You start with the, what is the height of this skip list? Let us say it is S3. Then you start from there, right? So you can see here, first you search whether it is equal. If not, you go for the next P. Next is, if there is an element in that particular list next to it, fine. Then you will search if they're fine. Otherwise, you go to below. And then I'll probably demonstrate the same here. You can just have a demonstration, then probably we'll discuss about it rather, right? You are searching for 78 here, right? You can see we have started from S3 here, minus infinity, 78 is greater. So we go below. See, first is compare it with the next. Next is plus infinity. Plus infinity, which is nothing but more, which is more than 78. So you come to below of it, right? Below of it is nothing minus infinity. Then you go to it next. Next is nothing but 31. 31 you can find is less than 78. Then you want to search for this 78. Then you probably go for the next in order to see whether it is available next. If it is not, then come to the below of it. Then again you search for the next one, which is equivalent to 78. If not, then move on to the next, right? If it is less, then move on to the next rather, right? So by being here at 64, you will compare with its next. But with its next, if you see it is plus infinity, which is quite higher, then you come to below of the same. Then you will then go to its next and then compare. You found it as equal. If it is equal, then you stop searching here, you return the element. So this is how basically the algorithm works. You can see the algorithm here. All of you can see the algorithm right here. We'll probably trace the algorithm now, which I have discussed before with one value 55. All of you can able to see, right? My screen is quite well legible to you rather, right? So if you look at the algorithm here, what is happening? You're searching for a certain key. Let us say, for example, 55 you want to search, right? What is happening here? You first see that if there is any element below to that, right? You start searching from, as I said, the highest skip list. You have sequence of list, right? The skip list is a sequence of list. The highest one is nothing but sh. So you start with sh. Your element is going to be found only at the s0. S0 consists of all the elements in the non-decreasing order, rather, right? So until you reach S0, you will have to search for the element, right? So how are you going to search it? Here the algorithm is given. You can see you check whether there is a below P. If there is a below P not equal to null, then you go to below first, right? When you start searching from SH, the next is going to be plus infinity. So you don't need to check that rather, right? You just go for the subsequent list below to it and see that if there is any list below to it, then you immediately move on to that list below rather. You can see here. Can you see? If below P is there, you go to below, right? You come here. Then while key after P is less than or equal to K, do. Here our key is, let us say, 55, okay? Key is 55. Key is 55. Now you are searching after P. After, by being here, what is after P? That is 17. You are comparing 17 with key. 17 is less than 55. Yes or no? If so, then what you will do? You go to the P gets after P. Do you have after P here? You don't have. So you come below. You come below. And then by being here, you compare, its value with 55, which is less. Then you go to its, you check with its next rather, right? Yes or no? You take the after P. You take the after P and then compare. You can find it is lesser. Then you take the after P. When you take the after P, which is lesser, so you will come below for it, right? Okay. Then you are comparing the next like that. You come below, then next, like that. There are two ways. It can directly go here. It is equal because here we have taken equal also, right? There are two cases. It may go like this or it may go like this. There are two possibilities in which it can be searched here. Okay, since we have given equal here, by being here, when it checks with the next element, that is found to be equal, so it can come below. And then next you don't have, come below. Next you don't have, come below. Next you don't have, so come below. And then this way, this is one way, and the other way around is it can be like this also. Either this way or that way. If you go, if you remove this equal, then if you remove in algorithm equal, then it comes like this. Otherwise, it goes like. There are two ways here in this particular. Let us first, trace this and then see with visualization how does it going to help you out in searching the same. I hope the algorithm is clear to all of you. Yes. Yeah. So what is happening here? You can see first you start with the highest skip list, right? Below P, you are checking below P. Below P is null, not null. Then what will you do? You go to below P. P gets below P. You can see, you come here, right? Next, after P, you are going to check. What is after P? After P is 17 here. What is your key? That is your 55. So 17 is less than or equal to key? Yes. True or not? Yes. When it is true, what is that you would do? P gets after P. Means P will take the value of after P, right? But then here, what happens is, after P is infinity, then you come back to its, when you go back again here, condition is going to be false here, right? Okay, condition is going to be false. You come back here again to the outer while loop. Then you will see whether you have a below P. Yes. Then you go to the next. You can see P below P. Then you will compare with its after P. If exists and its value is less than our 55, then yes, it will take, right? P gets after P. Then you are going to compare with its after P, which is equal here. So in this case, this is true. But then here it is going with the first way of searching, the other way around, right? It is going with below here. Fine. But you can rather implement in the two fashions here. There are two ways, of course. Fine. So now it comes to the below and then checks for the after. After value is again less than the 55. Then you can see it goes to the below and then check with the after P. After P is less than the 55. Then it goes to the next, since you have next element which is less than 55. And then you have after P, but then equal. Even if equal, then you come to the below of the element. If there is a subsequent skip list below available, then you compare with its next is found to be less, then move to the next, and then it is found to be equal, so you stop doing it, right? That's how you are going to get the element. Oh, sorry, you were searching it for this case 55 rather, right? Sorry, 50. Yeah, 50 you are searching, sorry, huh? Just take key as 50. So what is happening? You go with here, then there is a subsequent list below to it. Yes, it is available. Then you are going to the next rather, right? And then comparing it with this after P. After P is less, so after P is less, you can see. So it goes to the after P, and then it finds the after P is plus infinity, which is not less than 50. So it comes to the below. If there is a below element, then compare it with the next. Next is less. So again, take that as P, going for the next P. Next P is found to be, we are checking for 50, of course, right? 50 less than 55 is true. Then you find whether there is a below. If there is a below, then you go to the next list available to below it. Then again you compare it with its after element is available, which is less than it. So you go there, and then you come to below, and then you compare it with its after P with 50, which is less. So you go there, and then you can find its after P is also less. So you can find P there, and then by being here, right? At 44, when it compared with the after P, which is greater, so it comes to below. If there is a skip list below to it, it comes to the below, and then it compare it with the after P. So now you can see after P is equal, so it stops. I hope this is clear. The algorithm is clear to all of you. Yes. Yeah. So this is how you perform the search operation. Now coming to the implementation, how do you implement the skip list? Since we need the list on the top, below, left, and right. So the node structure, if you probably look at, node structure consists of 4 pointers. Unlike our simple single linked list, in single linked list, you will have only one next pointer which will hold the address of the next node. In double linked list, what happens? You will have 2 pointers. One pointer, which we call it as prev. Pre pointer will hold the address of the previous node, and next pointer will hold the address of the next node in double linked list. But then double linked list is also not sufficient here to not implement skip list, since you have a sequence of lists of linked lists available for us, and which helps us to, which should give us a provision to move to the top, bottom, left, and right. So we need the net structure consists of 4 pointers in addition to the data, right? This is your key. In addition to the data, you will have 4 pointers. One pointer to go for the skip list available above to it. One with which you can probably go to the next. One with which you can go to the previous or predecessor, and one with which you can go to the below of it, right? So we can implement with the help of quad node, right? So quad node data structure we probably here implement, which is a self-referential, of course, like how we have it for linked list. Okay, so insertion and deletions operations, we probably see here. How does you're going to perform? So in order to perform the insertion operation or deletion operation, for both the operation, you need to first go for search. Searching is a basic operation here. You need to perform, rather, right? So that we have seen before, right? This is how you're going to perform the search operation. So first you need to perform the search and then find the room for the node you want to insert or you want to delete, rather, right? Then you can go for the insert or delete operations, right? So for both of them, of course, this search plays an important role. Once the searching is done, what is that you have to do? You have to simply insert a new node before to it. When you are inserting, you need to give the links and restore the links with its neighbor nodes. Neighbor nodes are going to be 4 of it, rather, right? If there is a below list, then you will get a pointer will hold the value of the below node, and if you have a list above to it, then the above node will hold the above pointer will hold the address of the above list, and if you have a next node as well in that list, then probably next pointer will hold the address of the next node. If not, then it will be null, rather, right? If there is no below list, then below pointer will be null. If there is no above pointer above list, then it will be the above pointer will be null. That way you will have, if there is a list to either of 4 sites, then its respective list address or the node available in that particular list whose address has to be mentioned in that particular pointer, rather, right? Otherwise it will be null. That's how the restoring of pointer values you have to do once after one finish doing this insertion or deletion. Fine. So to insert an element, we use a randomized algorithm here. We repeatedly toss a coin until we get tails, and we denote with I the number of times the coin came up heads. If I greater than h, we add to Skiplists new list as a new list, s of h plus 1. Okay, it's a probabilistic search, right? As I said in the beginning, this skip list is a probabilistic search mechanism, right? So here, how many do we have to insert in the same, or we have to consider it as a head? Because here you can see there are head nodes. For example, if you consider this particular skip list, the bottom list which will have the actual elements, rather, right, in the non-increasing order of the elements, but above it, if you see, these are said to be the head nodes, right? And above to it, you can see the number of head nodes, right, rather required are going to be listed out in the above list from the bottom, if you see, rather, right? Fine. In binary, when you are implementing binary search or a simple linked list, when you talk about, right, when you talk about a simple linked list, this is a simple linked list, the bottom which you can find list of all nodes being connected with each other, rather, right? But then you may have seen these head nodes. These head nodes basically helping you out to skip certain elements from being compared. That's how we name it as a skip list, rather, right? Fine. Why you are saying it is a skip list? Because you are skipping some of the elements from being compared based on these head nodes, rather, right? When you want to search for a certain element, see, for example, here in this case, the same example is given. 50 you are searching for, let us say. Okay, what is that you are doing? You're starting from the top list and then comparing it with 17. When you are comparing it with 17, when you found that your element is greater than 17, what is happening? You're immediately going for the next head of it, rather, right? So when you go to the next head, you are not going to compare the elements which are before to it, rather, right? You're skipping the element before to it from being compared. So this is how the lists are said to be the skip list, because you are skipping certain element from being compared by just comparing the head. Even in binary search, you do the same thing. In binary search, what do you do when you are given a key? You will first find the middle element of the array. Yes or no? You will first find the middle element of the array. when you and you compare your key with the middle element. When your key is found to be less than the middle element, you will go into the left half of the array. By skipping the right half of the array, you don't move into the right half of the array. It means half of the array comparisons are being rescued from being compared. Yes or no? There also you are doing the skipping process, right? Because the precondition for binary set. What is the precondition for binary set? The elements are required to be sorted first. They should be in the non-decreasing order. They should be in the increasing order of the elements, right? So when you are taking the middle element and then comparing your key, obviously if your key is found to be lesser, then definitely it can be found in the left half of the middle element. So why to search in the right half? That's how you are skipping from comparing rather, right? Even binary search you are doing the same thing. But then in skip, it's a little advanced than binary search, I can say, because you have more than one head. Okay, there you have only one middle element, but then you have more head. So with the help of this, what is that you're going to do is you're going to skip the elements in more than what do you say, by more than bytes, the other way around, quadruples, or you can say octuples. So that way means in the form of power of 2, you are trying to reduce the elements from being compared here in skip list. The other way you can say it is very similar to that of binary search only, rather, right? Complexity wise, if you see, it takes logarithmic, right? As I said, it is a probabilistic search. Fine. Whether to go for a new list to be generated across that particular list of skip lists already available, you will be doing it with the help of by tossing the coin, as I said, right, in insertion algorithm that we have discussed before. Is it clear to all of you? Is this clear?